Today I thought I'd spend a moment looking at moments. And moments is just another word for turning forces, or something wanting to rotate, or not, as the case may be. Now, to calculate a moment equals your force times your perpendicular distance. Or it could be your perpendicular force times your distance. And let's just do a little kind of example of a pivot, which have a nice green thing. And what we care about is the force acting downwards. And this being your distance. Now, let's just say, for example, the force wasn't acting downwards. It was, say, acting like that way. What we'd have to do is you'd have to look at your different components of it. And this is a right angle triangle. You might have an angle, and you might have to use SOHCAHTOA. So let's say that's X, or that's F cos X, and this one is F sine X. But we're not going to really worry about SOHCAHTOA today, so I'm going to just delete that and just assume, I'll delete some of the line, that, let's change to green, we can imagine going along like that, and then we have a F. Now let's have a little really simple example of a 20 Newton force is 3 meters away from the pivot. What is the size of the moment? Well, this is a simple, your moment equals 20 times 3, which is 60. In units is newtons times meters, which is Newton meters. Has gone to the swimming baths, although actually this has to be his own private pool at the moment because they're all shut. But anyway, things might change in a few months' time. This he's gone to the swimming pool and he's on a diving board about to jump into the pool. And this is a pivot, and this diving board is being balanced by a force downwards, force F, to counteract the mass of and the mass of the diving board. Or in reality, not mass, but more like the weight. So I am assuming is on a planet called Earth, although he might not be, but let's just assume he is for now. And we actually kind of need to work out the force of otherwise known as the weight of as well as the weight of the diving board. So the diving board has a mass of 20 kilograms, and has a mass of 100 kilograms. Find the force F given the system is in equilibrium. So there will also be some force coming up here to support the whole system, but we're not going to worry about that at the moment. And I'm also assuming that the diving board the mass is evenly distributed, so that the centre of mass of the diving board is in the middle of the diving board. So my first thing is I'm going to go in purple. Everything I'm going to write from here, I think, on this question will be purple. So when I look at this, how long is the whole diving board? Well, the whole diving board is 0.5 plus 1.5 meters, which is 2 meters. And the middle is going to be 1 meter from the edge. So middle is one meter from either end. So let's just have a, it's not going to be perfect to scale, but I'm going to say we've got some force acting down there, and that's going to be 0.5 meters, because we've got 0.5 plus 0.5 gets us 1 meter. So the mass of the diving board we can assume to be half a meter from this pivot, and it's all going to act downwards. We've also got some force here acting downwards. Now we're going to use F equals mg. Your force equals your mass times your gravitational field strength. Field strength. It's always quicker to say that one than it is to write it. Now on Earth, that's 9.8. We'll say 9.8. Or we could say 9.81. Let's go 9.81 newtons per kilogram. In reality, you more accurately say 9.8065. But even that, it does change a little bit if you're near a mountain, or if you're on the International Space Station, it's going to be about 9 rather than 9.8. And if you're on Mars or another planet, you just happen to be there, then it's not 9.8 either. But we'll just say 9.81 just to whatever. So the diving board is going to have a force acting downwards of, we're going to write just 20g. 20 times 9.81. And this is going to have 100g. 100 times 9.81. Now, when you've got moments, it's always good to kind of have a positive and a negative. So I'm just going to say this way round is positive. So anything trying to rotate this way will be positive. Anything trying to rotate this way will be negative. So you have that way round is negative. So this force, for example, is negative. Or you can view it as negative. Or you can say this distance is negative. It's often easier actually thinking of distance rather than a force being negative. Because they're all acting downwards, but you've got differences with your force. Now, there's one key thing, and that is the sum of your moments equals 0. The word sum just means to add. So the way we do it, I've zoomed out a little bit, is I'm going to say, let's go back to purple again. I don't know this F. This F, I'm going to do F times minus 0.5. So that side's minus, and this side's going to be plus. Plus 0.5 times 20g, because that's 0.5 meters times by 20g. And then I've got a plus. Well, how far is it from there, the pivot, to well, that's 1.5 times 100g, and that equals 0. So I'm going to scroll down, got a bit more room. So we have minus 0.5 f, so that's f times minus 0.5. 0.5 times 20 is 10g, plus, and g is just 9.8. 1.5 times 100 is 150. G equals 0. Now I'm going to group those together, and I'm also going to take get rid of this minus 0.5f. I'm going to take it to the other side. So 160g equals our wonderful 0.5 F. I don't like this 0.5, so I'm going to effectively either divide by 0.5 or times by 2, so that you get 320 G equals our F, or F equals 320 times 9.81, which I need to get my calculator out quickly, because even I can't bother to work that one out. I should have worked this out a little bit before, but it doesn't matter. And you get 320 times 9.81 is a nice 3,139.2 newtons. And that's how you work out your F. So you look at your moments, and the sum of your moments equals 0. And then what we do is we then work out each of our moments, add them together, and that equals 0. You can view it, say this way is negative and this way is positive, and then downwards being negative, up, or positive, different way rounds. As long as you define which way is which, you should get the same value. Okay. So let's have a little look at another question. This one here, we have a shelf, and it's going to be supported by 2 forces at either end. It could be wires, it could be whatever whatever the shelf is. And on that shelf there is a box of 10 kilograms, and it's 20 centimeters from the edge, and the shelf itself has got a mass of 30 kilograms. Now the first thing really we want to do is make sure our units is in the right unit. So here we have centimeters, but we don't really like that in physics. We actually like meters. We want everything to be in meters. So 20 centimeters is 0.2 meters, and 60 centimeters is 0.6 meters. We then need to think about all the forces involved. So with F1, F2, we have a force pulling it down here. Well, this box has got a mass of 10 kilograms, and we're going to use F equals mg. Our force from gravity, our weight, is our mass times our gravitational field strength, and we can just write 10g, just to save us writing 10 times 9.81. We then need to think about the shelf. Now the shelf is a uniform shelf, which means its mass is evenly spread across the entire shelf, and therefore we can assume the centre of mass is in the middle. I'm going to say here, and that is 30g. And this entire length from there to there is in the middle of our shelf. Well, how long is the shelf? Well, the shelf is 0.2 meters from this F1 to the mat, to the box, and then we have another 0.6. So the total shelf length is 0.2 plus 0.6, which is 0.8 meters. And the middle of the shelf is 0.8 divided by 2, which is 0.4 meters. So 0.4 meters is from the F1 to the middle of the shelf. Now another thing I'm going to quickly do before we do any calculations is define which way is positive. So I'm going to say this way is positive in terms of our direction, and I'm going to say downwards, that's not narrow, it did something weird there, downwards is also positive in terms of our force. So I would expect F2 and F1 to be negative values for F, just because of the way I've defined it. They might in exam have it where they just want the magnitude of it, and then we kind of ignore the negatives when we get to the final answer. So our sum of our moments equals 0, and a moment equals force times distance. And all the forces are perpendicular to where the pivot are, so moment is force times distance. So I'm going to take moments around F1. So zoom out a little bit, and I'm going to go F1 times 0. So we're looking at going, how far away is F1 from F1? Well, it's nowhere. So that's F1 times 0 plus 0.2 times 10g plus 0.4 times 30g, and then we have 0.8, so plus 0.8 times F2, and that equals 0. So this bit is 0. We have 0.2 times 10 is 2g, and then we have 0.4 times 30 is 12g plus 0.8 F2 equals 0. And if you notice here, now the F1 has disappeared. What I'm going to do is group those together. 14g plus 0.8 F2 equals 0, and I'm going to take away the 14g, so 0.8 F2 equals minus 14g, and therefore F2 equals minus 14g over 0.8, which, if you happen to have a calculator, you got 14 times 9.81 over 0.8, which is 171.675. And I have had that prepared in a calculator just before. This is like the third attempt at doing this without fluffing the wordings. So, and that's in newtons. Now there's a couple of ways. Oh, there's a minus. I forgot to put the minus in. There we go. Minus 171.675. So if I zoom out, and we've got to that point so far, I'm going to just put a line because we're going to run out of room otherwise. And I'm going to do some working on the other side. So there's a couple of ways we can go about to work out what F1 is. We could take moments around F2. But another way is the sum of the forces equals 0. So this is where the shelf is not moving, it's not accelerating, it is stationary. Well, I'd hope so, at least, otherwise the box isn't going to stay on the shelf very long, and therefore the sum of the forces is 0. Now we have F1 plus 10g plus 30g plus, well, what's our F2? It's a minus. So actually I'm going to delete that there, minus our 171.675 equals 0. Well, what does F1 equal? Well, F1 is 100, we're going to chuck everything the other side, so 171.675 minus 10 times 9.81 minus 30 times 9.81. So that's minus 10g minus 30g. So F1 equals, I'm going to minus 9.81. I'm just quickly typing that calculator. So F1 equals minus 220.725 newtons. So that's our two forces, F1 and F2. Here we have 4 questions for you to have a go at. Feel free to pause the screen, and then you can have a go at them on a piece of paper. And I'm going to just zoom in now on each of the questions, give you a bit of better view depending on what screen size you're actually viewing this on, and then read them out. So, question 1. The nut needs to be tightened to a torque of 120 Newton meters. what is the magnitude of F. That's a spanner in a nut. So here we have and Anne. They're going swimming in their own private pool because all the public ones are shut, and they have their own diving board. The diving board has a mass of 50 kilograms, and the mass is uniformly distributed across the board. Has a mass of 80 kilograms, and he is at the end of the board. Find force F. And hopefully is not going to jump onto Anne, but we might see. This is Now is walking across a 20-meter bridge, and is currently 4 meters from F1. The bridge's 200 kilogram mass is evenly distributed across the length, and has a mass of 100 kilograms. Find the magnitude of F1 and F2. And finally, we have a shelf. Now that shelf is balanced by a little pivot and a force of 200 newtons. So the shelf has a mass of 10 kilograms and is 2 meters long. The 20 kilogram mass is distance d from the pivot, such that a 200 newton force is on the end, puts the system in equilibrium. Find distance d. So I'm going to zoom out and have a little go at those, and in a moment we'll have a little work solution for each of them. Hi guys, just a little shout out before I go into the solutions to the questions. Just a little call out to basically, if you like so far, please subscribe. And if you're willing to help out a little bit during these times, please consider signing up to Patreon, patreon.com/MP the tutor. And then you can help either buy some hand wash, buy some loo roll, and you can also buy some new books. Also, a little special offer is if you do subscribe, I'll be sending out some notebooks to any, whether you sign up just for £3 a month, I'll send you out some hardcover notebooks. These are custom designed, which I made a little while ago for all my students. So please consider subscribing, and please consider just putting £3 a month towards making these videos. Much appreciated. Hope you get the right solutions and right answers. Here we have a spanner, and the nut needs to be tightened to a torque of 120 Newton meters. What is the magnitude of F? Now, the torque is another name for your moment or force times distance. So your torque or moment equals your force times your distance. And sometimes you can actually look at the unit. So newtons is force, meters is distance, and they are times together. Now, one of the little things we have to do is make sure we're in the right unit. Here we have 40 centimeters, and we then need to make sure that's in meters. So 40 centimeters, 0.4 meters. Now, what we need to find is our force, and the moment equals your force times your distance. So to get force on its own, we're going to divide by the distance. So your force equals your moment divided by your distance. So in terms of what we want 120, got a wrong pen, 120 divided by our 0.4. Which, if we use a calculator, you get a nice answer of 300, and this is a force, so it's newtons. So our force required for this spanner is 300 newtons. Here we have and they're in their own private swimming pool. And they're in the same family, so they all can all swim together. And is about to dive off the diving board, and the diving board has a mass of 50 kilograms, and its mass is uniformly distributed across the board. Has a mass of 80 kilograms and is at the end of the board. Find force F. So first of all, we're going to define which way is positive. So I'm going to say this way is positive and this way is negative. So make sure it looks like positive. I've zoomed out a little bit because so we can give a bit more room to answer the question. And I'm also going to say downwards is positive. So it doesn't really matter. You'll get the same answer. But it's kind of like we need to make sure we define which way is positive and which way is negative. We then need to make sure our units are the right units. So here we have 40 centimeters, and we don't want 40 centimeters, we want that in meters. So that's 0.4 meters and 1.6 meters. We then need to think about, well, our forces. So yes, we have this force F, but we also have the force of the weight of the board, and we're going to use F equals mg, where g is your gravitational field strength and m is the mass. And our gravitational field strength on a planet called Earth is about 9.81. So what we then do is we need to think about, well, the board. The board's mass can be assumed to be in the middle, and the entire board is 2 meters long, and therefore the center is 1 meter from the edge. But I want to know how far it is from here to here. Well, from the pivot to the center of mass, and I'm going to say that's 50 g for the force, well, you have to do 1 minus 0.4, which is 0.6. So that's 0.6 meters. We also have R. Now R is got a mass of 80 kilograms, so his weight is 80 g. We then now have all our forces. We could have this one here, which I can call big force or something big. I'm going to call that big force because that's the biggest. It's all supporting it, but we kind of we might as well include it. So we're going to call it a big force. So then we look at our moments. So we have F times by minus 0.4 plus big times by 0 plus 0.6 times by 50g, and then 1.6 plus 1.6 times 80g. We're going to use our calculator a little bit here, may as well, and you get minus 0.4f. The 0 times the big just disappears, so anything times 0 is 0. We then have plus 0.6 times 50 is 30g, and then we have 1.6 times 80 is 128g, and that equals 0. I forgot to put that. So our sum of our moments is 0, and therefore what I'm going to do is move that up a little bit. We've got our 0.4f. I'm going to bring the 0.4f to the other side by adding it, and we're going to group these 30 plus 128. So 30 plus 128 is 158g equals 0.4f. What we then need to do is quickly make sure I've got a calculator ready. We're then going to divide by the 0.4. So our F is 158g over 0.4, or 158 times by 9.81 over 0.4. Quickly type in a calculator. 158 times by 9.81 divided by 0.4 gives you a wonderful 3,874.95 newtons. Zoom out. There we go. Just about fitted it on the page. So the force F is 3,874.95 newtons. The big force, if we actually wanted to work out the big force, which we don't, but if we did, well, big, I'm going to write big, actually has to be equal to all these other forces pushing down. That's why it's called big. So our big force in this case, which isn't part of the question, but we might as well work it out, is 50G plus 80G plus our 3,874.95. So I'm going to just put plus 130 times 9.81, which big equals 5,150.25. And I'm going to put a little star saying not part of the question. But hey, thought we might as well work that out, or why not? Cool, so let's move on to the next question. So is walking across this 20-metre bridge. He's not very happy at the moment. I think and helped build it, and they're not confident on their building skills. But anyway, so he is currently 4 metres from F1, and the bridge's 200 kilogram mass is evenly distributed across its length. And has a mass of 100 kilograms. We want to find the magnitude of F1 and F2. So first of all, it's a good idea, like I said last time, just to define which way is positive and which way is negative. So I'm just going to say this way is positive, and I'm going to say downwards is positive as well. Just, why not? May as well. You still get the same value. So let's look at this system. Well, we've got F equals mg for our weight, and we need to have the weight of being a wonderful 100 G, 100 times 9.81, because his mass is 100 kilograms. We also have the bridge's mass. So the bridge's mass is 200 kilograms, and therefore its weight is 200 G. And we're going to assume that the mass of the bridge is at the center of the bridge, because it's evenly distributed across the whole bridge. Now, from to the F1 is 4 meters. And our center of mass to F1, nice straight line, is a nice 10 meters. And we have the entire bridge, which is, I'm going to have to do at the bottom, may as well. The entire bridge is 20 meters. And what we're going to do is, I'm going to zoom out a little bit, so we'll get the whole thing in. I'm going to take moments around F1. So I'm going to use F1 as my pivot, and I'm going to assume it's all going to try and rotate like that, up and down, around those pivots. So we have F1 times 0. So our force F1 is 0 meters from F1. We then have plus 4 times 100G plus 10 times 200G plus 20 times F2, and that equals 0. So F1 times 0 is 0. We have 4 times 100 is 400 G plus 2000 G plus 20 F2 equals 0. Let's move down a little bit. So what I'm going to do now is we have that 400 plus 2000 is 2400. And I'm going to take it to the other side. So 20 F2 equals minus 2400 G. So our F2 is our minus 2400 G over 20, which is a wonderful 120 G, which we might as well, and there's a minus there, 120 times 9.81 gives you minus 1172.77. Let's me edit it. Let's undelete that one. 77.2 newtons. Now, the question is asking for the magnitude of F1 and F2, but here we have just a negative value. So the magnitude doesn't care about the negative of fine of F2 is 1177.2 newtons. Don't worry if you end up using 9.8 or 9.81, there'll be slight differences. What we then have to do is our sum of the forces equals 0. So we have 100G going down, we have another 200G going down, we have F1 and F2. So F1 plus F2 plus 100G plus 200G equals 0. Now, I know my F2 is minus 120G, so we've got F1 minus 120G plus 100G plus 200G equals 0. 100 plus 200 is 300 minus 120. So F1 plus 180G equals 0. F1 equals minus 180G. And the reason why it's minus is if downwards positive, upwards is negative. And therefore that equals do 180 times by 9.81 gives you a minus 1765.8 newtons. Now the magnitude of F1, ignore the negative, so it's 1765.8 newtons. Cool, and then we'll have a little look at the next question. So here we have a shelf. Now the shelf has a mass of 10 kilograms and it's 2 meters long. The 20 kilogram mass is at distance d, such that a 200 Newton force at one end puts the system in equilibrium. Find the distance d. So we're also assuming this shelf has got a uniformly distributed mass. And we need to actually do a few little things first. Well, first of all, I'm going to define which way is positive and which way is negative. I'm going to say this way is negative and this way is positive, may as well. And we need to convert the 60 centimeters into meters. So that's 0.6 meters. And we also need to look at this force here. So this has got a mass of 20 kilograms, but its force or its weight is 20 G, or 20 times 9.8. We also have the shelf, and the shelf has a mass, and its mass is 10 kilograms. And we need to have a weight of 10 G. But how far from the pivot is it? Well, the shelf is 2 meters long, so I'm going to assume that the center of mass is in the middle of that. So the middle of 2 meters is 1 meter. So it's going to be 1 meter from the edge. But this from here to here is 0.6. So from here to here is going to be 0.4. So I'm going to rub that out. So from our pivot point to the center of mass of the actual shelf is 0.4 meters. We're then going to do some of our moments. So the sum of the moments equals 0. So we have we might as well just go crazy and call that one big again. Might as well. Just so that you know that force is there. We have 20 G times by minus D, because our distance is negative, plus, well, 10G times minus 0.4 plus big times 0 plus 0.6 times 200 equals 0. Well, what do we have? We have minus 20 GD, and that's just a number, so we could sort that out in a moment, plus, well, 0.4, actually not a plus, it's a minus. Just be careful, we always do that, like we always make mistakes, like negative turn to positive, positive turn to negative. So minus 0.4 times 10 is 4G, big times 0 is 0, and then we have to go add our 0.6 times 200 is 120 equals 0. Now, I'm going to actually convert all these into numbers because may as well. So we have 20 times 9.81. So you've got minus 196.2 D. And then we have 120 minus our minus 4, so 120 minus 4 times 9.81 is 4 times 9.81 is going to be 80.76. So that's plus 80.76 equals 0. We're then going to move this minus to that side, so our 196D goes to the other side. So 80.76 equals 196.2 D. And therefore D is, we're going to divide by the 196.2. So it's 80.76 divided by 196.2, which is equals that divided by 196.2. Gets your wonderful 0.4116 meters. There we go. And that's our answer. So how big is D? Well, that's 0.4116 meters. You could round that to 0.412, or that's not nor 0.412 meters. If we wanted to add up figure out what big is, our big force pushing up at a pivot, we would just add our 20G plus our 10G plus our 200 newtons together, because that's all our forces going down. We have one force going up, and therefore the big must be the same as all of those added together. But we're not going to worry about that. Cool. So hopefully you got most of those correct. If you use 9.8 rather than 9.81, your values will be slightly different, but you should have the same method. Hi guys, if you've enjoyed this video, please consider subscribing or even helping me a little bit on Patreon. It's patreon.com/MP the tutor, and this helps me make some more videos and dedicate a bit more time, and you can help by some hand wash or some loo roll, and I'm also sending out some free books, so up until the end of April, no matter which one you sign up for, I'll send you out a hardcover 192-page custom design notebook, and potentially a few. I'm hopefully just going to make a couple of videos a week, just to support as many people as I can, whilst everyone's off school for the next 6 months. thank you very much, and have fun watching these videos and having a go.